consider the differential equation dy by dx equals xy, where x and y are both non-negative, so both greater than or equal to 0. Verify that y equals c e to the x squared over 2 is a general solution for any constant with real c, where c is also non-negative. Part B, construct the slope field using integer grid points for x and y are between 0 and 4, including 0 and including 4. Okay, so that means we need to start with probably at 0, 0 and go all the way up to 4, 4 and everything else in between and find the value of dy by dx at all of those different points. Part C, sketch the particular solution curve through P21. We're going to do that using the slope field. Part D, verify algebraically that the curve you sketched is y equals 1 over e squared e to the x squared over 2. So that will be just finding the particular solution that goes through 2, 1. And part E, draw isoclines corresponding to k equals 1, 3, and 6. When it says k, that means the gradient, dy by dx equals 1, dy by dx equals 3, dy by dx equals 6. It's literally just joining all the different points that have gradients of 1, that would be one line, of 3, that would be another line, and 6, that would be a third line. But it would probably make a lot more sense if I actually draw the slope field and then talk about it then. So we start with part A, which says verify that y equals c e to the x squared over 2 is a general solution to dy by dx equals xy. So basically, we can start from the y equals c e to the x squared over 2, and we can differentiate and get back to xy. Y equals c e to the x squared over 2. So dy by dx, well, you need to, for any exponential function, if it's a function of a function, then you need to look at that power and differentiate that with respect to x. So if you had x squared over 2, well, dy by dx would be 2x over 2, which is just x. So the x comes as a multiplier at the start, so x c e to the x squared over 2. Right? Now, if you look at that, we're supposed to show that this equals xy. So this is obviously x. And we were given in the question that y equals ce to the x squared over 2. So that is y. Okay, now we just need to deal with this bit of c being greater than 0. So we're told that x and y are both non-negative, which means that dy by dx could never be negative. So if we think about e to the x squared over 2, or if we just take the x, so x squared is going to be greater than or equal to 0 for x greater than or equal to 0, as we've been told that it is here. So x squared over 2 will definitely be the same for x greater than or equal to 0. And then when we raise e, which is a positive number, around 2.72, so e to the power x squared over 2 is also going to be greater than or equal to 0 for x greater than or equal to 0. So as y equals c e to the x squared over 2, and we also know that y is also non-negative. So as y, which equals c e to the x squared over 2, is also non-negative, c must be non-negative as well. Because if it wasn't, then it could turn this whole thing negative if c was negative. So therefore, y equals c e to the x squared over 2 is a solution for all real c where c is greater than or equal to 0. For real c where C is non-negative, greater than or equal to 0. On to part B. Construct the slope field using integer grid points for x and y are both in the closed interval from 0 to 4. So it closed, so that means it includes 0 and it includes 4. So we need to consider all integer combinations of x's and y's between 0 and 4 inclusive. And we need to decide what is dy by dx for all of those combinations, which will be quite easy because dy by dx is just x times y. So if x is 0 and y is 2, it would just be 0 times 2, and so on. So the most efficient way to do this is to begin with a table and then we'll draw a graph. Okay, so we construct a table. So the x values can be 0, 1, 2, 3, or 4. The y values can be 0, 1, 2, 3, or 4 as well. So we have a nice table like this. Nice, it's probably not going to be that nice. Draw around. Okay, so these are our x's, and then here are our y's, and then in the space in the table we just have dy by dx, which is going to be x times y, because we were told that dy by dx equals xy. So we just times them together. So if x is 0, then whatever the value of y is, dy by dx will be 0. So we can put all these zeros down here. You can have exactly the same reasoning for if y is 0, so if y is 0 on this top row, and so everything else, if x is 1, then dy by dx is just going to be y, so it would be 1, 2, 3, and 4. If y is 1, exactly the same, 2, 3, and 4. If x is 2, then we can just double the y's, so 4, 6, and 8. Y is 2, we can have a 6 and an 8. If x is 3, you're going to have 9 and 12. If y is 3, you're going to have another 12. And then if they're both 4, you're going to have 4 times 4, 16. Okay, so that gives us the values of dy by dx for all of these different integer points. Okay, I will draw my axes properly. So I'm going to have the x-axis here and the y-axis going up like that. So we've got the x and the y. So then we need to put some points on. We need to get to 4, so that can be 1, 2, 3, and 4. Same for the y's, so 1, 2, 3, and 4. So then we just need to think about the different gradients at those points and try to represent them using a straight line. Okay, so all of the points where dy by dx equals 0, well, a line with a gradient of 0 is just a horizontal line. So on the axis points, I can just draw a little line like that to represent the gradient being 0 at these points. Remember, it's just a little short line. And this is basic, this bit here, for example, it's telling me that at the point 0, 1, dy by dx is 0. Now you can do the same along the x-axis because the point 1, 0, 2, 0, 3, 0, and 4, 0, at all of those points, dy by dx is 0. Okay, so that's the fairly easy bit. What gets difficult is when you have to distinguish between a line with gradient 12 and 16, so you just have to kind of get the scaling right-ish so that you can allow for steeper lines. So now I'll try and put the ones in. So a gradient of 1, if you scale your axes evenly, that's a line with 45 degrees. So that happens at 1. So at 1, 1, we're going to have a little 45-degree line, something like that. Okay, so at 2, 1 and at 1, 2, I have gradients of 2, so I can kind of use the squares to do that. So that's the point, 2, 1. So it would go from there along 1 and up 2, so I kind of, that's my basic angle, something like that. Same at 1, 2, it would go along 1 and up 2, so point to there, something like that. 3, 1 and 1, 3, I've got a gradient of 3. So that would be going along 1 and up 3, 1, 2, 3. So point there, something like that. It doesn't look a lot steeper than the 2, but it should be. At 1, 3, again, you're going to go along 1 and up 3, up to there. So something like that. And that one definitely does look a little bit steeper. Then you've got gradients of 4 at 4, 1, 1, 4, and 2, 2. So if we find 4, 1, along 1, 1, 2, 3, 4, kind of point at that. Something like that. 1, 4, so over here. Again, along 1, 1, 2, 3, 4. Kind of point in that direction. Go a bit further. And at 2, 2 is here. 1, 1, 2, 3, 4, like that. So point at that one. You can see the slope field sort of coming together. Now we've got gradients of 6 at 2, 3, and 3, 2. The 3, 2 is over here. So 1, 2, 3, 4, 5. Got to kind of point at this dot over here from 3, 2. And the same from 2, 3, which is over here. So 1, 2, 3, 4, 5, 6. If I point over there from 2, 3, something like that. Then we've got gradients of 8 at 4, 2, and 2, 4. So this is probably the last line I can actually draw by putting dots on. So along 1, 2, 3, 4, 5, 6, 7, 8. So if I can point up to there, something like that. The same for 2, 4. So I'm not going to be able to do 1 and 8, but I could do a half and 4. 1, 2, 3, 4. So if I kind of point up to there, that should be okay. Okay, something like that. So you can see a field is coming together slowly. Then we've just got 9, 12, and 16. So the 9 happens at 3 and 3, which is here. Which is here. So that's going to go along 1 up 9. 1, 2, 3, 4, 5, 7, 8. Now just fit that on. So if I point up to there from 3, 3, you see the lines really are getting quite steep now. Then I've got gradients of 12. That's 4, 3, and 3, 4. So that is here. And here 3, 4 is around here. So gradient 12 is along 1 and up 12. See, that's probably not going to work. So if I just draw the 16 at 4, 4, which is up here, just draw that really vertical. And the 12 is probably pretty similar, really. And there's another one here. So then what we have is a slope field. So for all the integer points, just get rid of all these little dots I've made. Okay, so then we are left with the slope field. Okay, part C. Sketch the particular solution curve through P2, 1. Okay, so we go to the point 2, 1, and then we sketch the particular solution by following the slope field. So we have not that many points. It took quite a while to do, but if you think that the more points, so say we'd gone every half instead of every 1, we'd have a much more detailed slope field, but it would take a lot longer and would be impractical to do so by hand. It was pretty much impractical anyway. But if we start from this point 2, 1, okay, so if I go to the right of this, you can see we've got quite positive gradients. They're going to get more positive. So it's probably going to do something like that. And if I go to the left, you can see the tangents are getting a lot flatter. So it's going to come around and get really quite close to being flat like that. Okay, so that's the sketch that's been done using the slope field. Now it says verify algebraically that the curve we have sketched is y equals 1 over e squared times e to the x squared over 2. Okay, so we know y equals c e to the x squared over 2, and we're interested in the point 2, 1. So y equals c e to the x squared over 2. So at the point 2, 1, y, which is 1, equals c times e to the 2 squared over 2. So squared, which is, so 1 equals c times, well, it's e to the 4 over 2. So that's e squared, c e squared. So then if we solve for c, well, c is going to be 1 over e squared. And if you look at what we're aiming at, there is our c, 1 over e squared. So that looks good. So y equals 1 over e squared e to the x squared over 2 is the particular solution. That passes through 2, 1. Right, just realised that sketching a particular solution was part C, and then doing the algebra bit was part D. So all that is left is part E, which is draw the isoclines corresponding to K equals 1, 3, and 6. Okay, so just to clear up this business with the K, for a first order differential equation, first order means you're given dy by dx, written in the form dy by dx equals hxy. So what that means is some function of xy is a gradient function. An isocline is a curve given by hxy equals k. Remember, hxy is dy by dx. So basically, dy by dx equals k. So we need to draw isoclines for k equals 1, 3, and 6. So we need to join all the points in the field where dy by dx equals 1, 3, 6. And so we need 3 separate isoclines. And this is going to be part E. Okay, so if we return to our slope field, well, we know that dy by dx equals 1 at 1, 1. Remember, dy by dx equals xy. So if you want some more points on that, well, you could just think of other combinations that times together to make 1. So 2 times a half is 1. So it could go through 2 and a half, or a half and 2, which would be up there. 3 times a third is 1. So it could go through 3 and a third, which would be over here, or a third and 3, which is over here somewhere. Okay, so you should basically be able to see the shape. The order of the shape is going to go through a quarter and 4 as well, for exactly the same reason, because quarter times 4 is 1, and 4 and a quarter. So now you can see that it's going to look like this. Okay, so that is the isocline for k equals 1. For k equals 3, we already have 2 points. We have 1, 3, and 3, 1. So 1, 3 is over here, and 3, 1 is over here. So we've already got those. Okay, another way of thinking about it, which should help if we can use the black line as a base. So for the black isocline, it was dy by dx equal 1. So that means xy, which is dy by dx, equals 1. So y equals 1 over x, which is the equation of the black line. So if we think about the isocline for 3, it's going to be xy equals 3 So y equals 3 over x. So if y equals 3 over x, well, if you compare that to y equals 1 over x, that's just going to be a vertical stretch scale factor 3. So all of these distances are going to be stretched up by 3. So this would be stretched up by 3 and so on. And so if you think about this, where the graph ends, we can bring that up by 3, something like that. So you could roughly get a point, so say at 2, and we could sort of triple that distance, so maybe that's going to be over here somewhere-ish. But it doesn't need to be exact, but it's going to do something like that. Okay, so that is for k equals 3, which is y equals 3 over x. The final isocline is for 6. So for k equals 6, so equals 6, that means y equals 6 over x because xy equals 6. So you know already we've got 2 points which are 2, 3 and 3, 2. So 2, 3, we know it's going to pass through there. And 3, 2, you know it's going to pass through here. And you just got to stretch it really. So if you think about that compared to the 3 one, it's just going to be doubled. So I reckon it's just going to sort of come something like this and then steepen up like that. So that is for k equals 6, y equals 6 over x.